Welcome. My name is Alan Prost, and I'm going to talk to you about volume ventilation of the lung today. This is part of the course of AMPH 221. Specifically, we're looking at to introduce you to the effects of resistance and compliance, and we're going to use a test lung model that I've actually demonstrated in a previous video. In this model, what we're going to do is we're going to mimic a volume ventilator. So we're going to push a volume of gas, and in this case we're going to say that it's 1 liter of gas, across a resistance into a test lung model. And in our test lung model we can vary things like the compliance. So that's the stiffness. This is the compliance is a relationship of the distensibility of the lung or the stiffness of the lung, and that's controlled by this spring. So we can vary that from a highly compliant model where the lung is easily distendable to a low compliance model where the lung is actually quite stiff. We can vary things like the resistance, and that's the effects of resistance are noted during times of flow. So that's what we're going to do, is we're going to look at this relationship of pushing a volume of gas into a model of a test lung. And this does have some relevance to us because this model is very representative of the actual human body in conditions where we're doing volume ventilation. So what happens? Initially, the volume ventilator is attached to the test lung. There's nothing occurring right now, so there's no breath being delivered. So our P1, or our mouth pressures, these are to represent our mouth pressures, and our P2 are alveolar pressures, or the pressures that are actually in the test lung itself, are in equilibrium. They're both at 0 right now. This is in a status state. There's nothing occurring right now. So if we look down at our graph here, our pressures, P1, that's right at the ventilator circuit before the patient, right at the mouth, is 0, and P2 is also at 0. Well, now we're giving some breaths. So we're actually pushing this volume of gas across the resistance and into the test lung. Now it takes pressure. You always have to have pressure go from high to a low to create flow, and that's represented by that V dot I'm trying to draw there. So we see that we have to create a pressure gradient. So you'll notice that our pressures here in P1 are higher than they are in P2 because I'm forcing air across this resistance, and that takes pressure. P2 also represents the amount that we've distended this spring. So we're stretching the spring out as we push the volume of gas into the test lung, and that's pulling our spring up a little bit, and that takes pressure to do that. All right. Graphically, the way we see that is mouth pressures are here over time, so the same amount of time on both. We see that pressure gradient increasing, and to a lesser extent we see the pressure increasing at P2 in the lungs. There has to be more pressure at P1 to create flow across the resistance into the test lung. I know I've said that a lot of times, and you're going to hear it multiple times. Now we've got more flow. The flow is accelerating. We've got a high pressure gradient across here, so the molecules of air or whatever gas it is are rushing across past our resistance into the test lung. So remember, resistance is a function of flow. We have to have flow for resistance to be noted. And we're pushing that gas into the test lung, stretching out our spring even more. So P2 is a little bit higher now because we've got higher amounts of volume into the mouth or into the lungs. So P1 represents mouth pressures. It's building up, and it's at a little bit higher level than P2 so that we can have a pressure gradient and flow. Here we've gone a little bit further on. We've put more volume in, so P1 still has to be higher than P2. So we're pushing those molecules past the resistance. Now we've got the lung is quite distended, so P2 is higher because we're pulling up on that spring even more. More time has progressed, so we see that we've got more pressure in P2 and P1. P2 is lower because it just represents this compliance or the distensibility of our test lung. As time progresses, now we've just about finished putting in our total volume of gas. So we're putting in a set volume of gas at a continuous flow rate. We've still got a little bit of flow going on, so gas is still going from P1 to P2, and P2 is quite high now because look at how much we've distended or expanded our spring. Now we've put the entire volume of gas into the lung and we're just holding it in there. So we put in 1 liter of gas into the test lung, but we're just holding it there. So the effects of resistance now are 0. There's no effect of resistance because there's no flow. So P1 and P2 are in equilibrium. They're the same pressures because they both represent lung pressures or alveolar pressures, and that is the amount of pressure that's generated by this stretching of the spring, which represents the distensibility or the elastic nature of the test lung. So graphically, what does this look like? Well, when we look at P1, the mouth pressures, initially we built quite a high pressure in our system. Then when flow stopped, just at that instant flow stopped, the pressure in our system dropped down. All right? This pressure gradient between, we call this PIP, or peak inspiratory pressure, and this pressure here, which we call P plat, are different. Okay? And that was because that was the pressure gradient required to overcome the resistance. So this pressure gradient from PIP to P plat is the pressure that are required to overcome this resistance at the peak flow. All right? Those are difficult concepts to come across. P2, you notice it just built up steadily until all the volume was put in. So this is a linear relationship in our test lung model. Compliance is a single number, so just as more volume went in, the pressures built up in the test lung until we put in the maximum volume, and then the pressures were stabilized. So in P2, they just build up until we got all the volume in, and they equal our P plat. So right now, with no flow, the P1 and P2 are equal. Well, let's look at this relationship some more. As if we just leave that volume of gas in there, there's no change, and we call this an inspiratory plateau. There's no change in P1 and P2. Because there's no change in volume, there's no change in flow. We're just holding the gas in the test lung. Now we allow the natural recoil of the lung itself, in this case due to the spring. In a human model, of course, the elastance is the nature of the lung, and it naturally recoils, allowing exhalation to occur. So we've got exhalation occurring, so gas flow now has changed direction from the lung towards the ventilator. Effectively, the ventilator just allows the gas to go into the atmosphere, so our mouth pressures are basically 0. P2, we still have to have that pressure gradient because we're going to have flow now from the alveoli, from our P2 towards P1 to overcome this resistance. So now that there's flow, we need a pressure gradient, and we can see that here. We can see that there's some pressure still in P2, our alveolar pressures, and there's really no pressure in P1 because that's just our atmospheric pressure. As we allow exhalation to continue on, you can see that there's less volume in the lungs, but there's still a pressure gradient. The spring is still pulling down on our test lung, forcing air out past the resistance, so we still need that pressure gradient. It's less now, so flow rates will be lower, but we still need that pressure gradient to push the molecules of gas across the resistance back out into the atmosphere. So this is reflected in our mouth pressures still being 0 right here, and we still have to have a little bit of pressure in our alveoli, P2, to create that expiratory flow. We still have even though now exhalation is almost complete, it's not quite finished. So we still have, it's a slow or a very small amount of pressure gradient, so the flow will be low, but we still have gas going from our alveoli out into the atmosphere. Exhalation is now complete, so P2, our alveolar pressures, and our mouth pressures are equal. And this is represented graphically by both the P1 being at 0 and P2 now being at 0 to show the end of exhalation. So we're ready to give another breath in a few seconds or so, depending on the rate that we're bagging our patient or ventilating our patient. Well, that's a lot of information to take into account. So let's look at this. What we want to do is we want to look at the effects of resistance and compliance. We know that resistance is only a factor when there's flow in our system, and compliance is related into the distensibility of the lung, which is controlled by this spring here. Okay? So variations in compliance only affect this pressure gradient in here, or our P plat. All right? As volume is pushed into the lung, pressure builds up until we reach this maximum pressure, which is related to P plat. So if we have decreased compliance so that the lungs are stiffer, so it takes more pressure to create the to expand the lungs, in this model we've still put in 1 liter of gas. We've still put in 1 liter of gas, so the volume that we put in are the same, but it takes more pressure to get that same volume in because the lungs are stiffer. So decreased compliance relates to a increase in the P plat. We didn't change the resistance or the flow rate in this diagram, so the pressure gradient between PIP to P plat is the same in both models. All right. So with just a decrease in compliance, what we see is PIP is higher, P plat is also higher than comparative models with a lower or a normal compliance. Now, that's a difficult relationship. If we had a higher compliance, that means the lungs now are more distendable, they're actually more flaccid, and when you blow up that balloon now, the lung, it's actually easier. So we're still putting in the same volume. We've put in 1 liter of gas into each one, but in this one, because we have higher compliance, the plat pressure goes down compared to our normal model here. So this pressure gradient here is a reflection of the compliance of our model, or the distensibility of the spring. Here we've increased the compliance, so it takes less pressure to get that volume of gas in. So this value is lower. We've got a decreased P plat. I haven't changed resistance or our flow at all, so the pressure gradient between the PIP and the P plat is the same in both these models. These are complex relationships, and I've built something to help you explore these relationships. We'll talk about that in a minute. So resistance, now we know, is affected by both the actual diameter of the endotracheal tube and the flow that's going across our resistance. So from our normal model, resistance is reflected in the variations in pressure from PIP to that P plat. Remember, this is our peak inspiratory pressure. It's really hard to draw on this with these little mouse, but this is our PIP right at this pressure right here, established by the dotted line. That's my peak inspiratory pressure. If I have increased resistance, so it takes I have a smaller diameter airway, I'm going to have an increased resistance, and I need a larger pressure gradient to get that flow of gas past that increased resistance. And this is reflected by an increase in the PIP. So that gap between the PIP and the P plat is larger. All right? So that this is increased. Okay? Now that's a complex relationship. We're looking at, with resistance, the gradation between PIP and P plat. You'll notice that in both of these, P plat didn't change because I didn't alter compliance. Well, you're thinking to yourself, how am I going to get all this straight? Well, to help you with that, I've built a more complex version of this model that we've just demonstrated here. So what we have here is a volume ventilator model. You'll notice the graphs look very similar. Here's our PIP established right here, and here's our P plat. We can adjust on this model the ventilator controls, the volume being pushed in. In our model we just examined, we put in 1 liter or 1,000 mils. Here we're putting in 800, and you can change that. The flow rate we've got set at 80. we got an inspiratory pause. That's the length of time the breath is held in there. This is the number of times it's delivered each minute. The PEEP is the amount of distending pressure in the lungs, and right now I've got that set at 0. Here's the controls that we're particularly interested in, and these are mimic the lung elements of our patient, the resistance and the compliance of their lungs. We're not going to worry about the exhalation factor right now. So here's the data that we can observe whenever we do put in a volume and we do change these ventilator controls. We're going to relate that back to our patient data. And what we're looking at particularly is the PIP and the P-plat at this time. So if I do things like, to go back to our model, if I lower resistance, so I'm going to change that from 5 to 2, what happens? You'll notice that highlighted in red, this becomes less of a factor. With lower resistance, the PIP is lowered. The P-plat stayed the same. If I increase resistance, make it say 5 or 8, the PIP is higher compared to the P-plat. The P-plat did not change. We didn't change the volume of gas we put in. We didn't change the flow rate or the rate that we put that gas in. But that, of course, would change or affect the PIP. If I change our flow rate, if I lowered it from 80 to 40 liters per minute, you see that it takes longer to put the breath in, but it takes less pressure. The pressure gradient from PIP to P-plat is altered compared to our original model. All right. So these complex relationships can be explored using this test lung model. And that's what I want you to do, is to actually experimentally change these different factors. We can do things like alter the compliance. If I decrease the compliance, that's making the lungs stiffer. You'll notice that with decreased compliance, the PIP and P-plat are altered. P-plat goes way up, and PIP also goes up, but the relationship between them stays the same. So I can change this back to 30 mils per centimeter, so more compliant. It's still only about 5 centimeters, or it's exactly 5 centimeters of water pressure difference between the PIP and the P-plat. I can even increase compliance even more. I can change it to, say, 40 mils. So the PIP comes down, the P-plat comes down, but the gradient between them stays the same. Okay, so those are the relationships I want you to look at and experimentally discover. To help you with that, what we can do is we're just going to shut down here out of this view, and to help you with that, I've built a table here which you can utilize to help you with those. I'm just having a little problem with my computer at this second. Okay, there we go. So we've set up our basic settings here. So we've established certain primary conditions. Now, before you alter each one of those, you want to make sure your virtual ventilator is set up with these controls, and then we'll get a PIP and a P-plat in results. Now, what I want you to do is to change the increased each one of these settings incrementally. So you're going to increase lung compliance. And what you could do is, because initially it's set up from 30, you could set that up to, say, 40. So when you increase lung compliance, what you should see, and you will see, is that the PIP will come down. All right? With increased lung compliance, it takes less pressure to put the same volume in, which you're going to leave at 500. So PIP and P-plat will come down. Now you'll also notice as we make further changes that the pressure gradient between the two will stay the same. So when you decrease lung compliance or make the test lung stiffer, PIP will go up and P-plat will also go up, but the gradation between them will stay the same. All right? So incrementally, before you make each one of these changes, all right, what you're going to do is you're going to make sure that the test lung is set up at the base settings, and then say, well, if I just change compliance, what would happen? Then turn it back to normal. if I just changed resistance, increased it or decreased it, what would happen? Set it back to normal, and if I increase tidal volume delivery or flow rate, what would happen? What am I going to observe just looking at these two parameters, PIP and P-plat? Build your table like this, be able to do the calculations and know these relationships. That's what I'm asking you to do. What I'm hoping you learned today is that during volume ventilation, where we give a set volume of gas, when there's flow rate going into the test lungs, we have to have a pressure gradient. The mouth pressures and the alveolar pressures must be different to allow flow across the resistance. Resistance will be affected by flow and the actual diameter of the endotracheal tube or the airways that we're pushing the gas through. We're going to look at the relationship of compliance, which related in our model to the extensibility of the spring. Graphically, you're going to understand how that works. You're going to see what we have an increase in pressures at the mouth, and then when there's no flow, that pressures will drop down to reflect alveolar pressures, P2. All right? So P-plat reflects the distensibility or the compliance of the lung. The PIP gradation to that PIP, to the P-plat, reflects the effects of resistance and flow. Those are complex relationships, and I think by utilizing the volume ventilation model and building your graph, you'll understand them. So, thank you very much. This is Alan Prost, instructor of AMPH 221, and we'll see you in class.